Hi guys, welcome to EC Chem videos back again for another important organic chemistry session. Today we are trying to focus on some reactions of carbonyl compounds, an important chemical compound we always come across in our syllabus. First of all, remember the reaction mechanism of carbonyl compounds is nucleophilic addition type of reactions. After this, we'll try to focus on more, as I said earlier, the reactions shown by both aldehydes and ketones. I'm taking for the discussion 3 reactions. First one is the reaction of aldehydes and ketones both with aqueous hydrogen cyanide HCN at the presence of, we have a KCN to be used as a catalyst. KCN breaks down in water and makes K plus and Cn minus. The Cn minus is acting as a catalyst in the reaction of aldehydes and ketones with HCN. Of course, the reaction has to be done in alkaline medium. And we go to the second reaction. Second reaction is reduction of aldehydes and ketones. But the reduction of aldehydes and ketones, we use some reducing agents. You will see that when it comes to the discussion. And in the third reaction, we see how aldehydes and ketones react with Brady's reagent, but commonly known as 2,4-DNPH. We can expand it, 2,4-dinitrophenyl hydrazine. It's a very, very special reaction under aldehydes and ketones. When it comes to reactions with aqueous HCN, at the presence of KCN in alkaline medium, some special thing happens here. The special thing is this: when these reactions happen, you get a compound called hydroxynitrile. Remember, aldehydes and ketones react with HCN to produce hydroxynitrile compounds. The specialty is this: these hydroxynitrile compounds have always one carbon atom more than the aldehyde or the ketone participating in the reaction. To explain this better, if you allow a 2-carbon aldehyde, ethanol, for example, react with hydrogen cyanide, you are going to get a hydroxynitrile compound having 3 carbon atoms. 2 plus 1 is 3. This added hydrogen is coming from hydrogen cyanide. You will see that when it comes to the reaction I'm going to discuss. And second example, if you react a 4-carbon containing ketone, it will produce a 5-carbon containing hydroxynitrile. What are these hydroxynitriles? A hydroxynitrile compound has a carbon atom which is bonded to one OH group and a nitrile group. As you can see in the diagram below, we have a carbon atom. You know, the valency of carbon is 4, so it makes 4 bonds around carbon. And on one side, you have OH group. And on the other side, we have a cyanide group. So this is a unique feature of hydroxynitrile compounds. They are going to produce by reacting with aldehydes and ketones. Let us try to discuss some reactions using both aldehydes and ketones. First, I will talk about the reactions of aldehydes with aqueous hydrogen cyanide. The simplest aldehyde we know about is methanol. Methanol has 1 carbon atom. And if it is reacted with hydrogen cyanide, what will happen? See the product. Product is hydroxyethane nitride. The structure of it is given here. What has happened, if you see clearly, see the carbonyl functional group here, carbon double bond oxygen. It is no more in the product. Carbon double bond has changed to a carbon single bond. And to this oxygen in the double bond, 1 hydrogen is coming. This hydrogen is coming from hydrogen cyanide according to the reaction I have shown. And to this carbon atom, which was in the carbonyl functional group, the hydrogen cyanide group is getting attached. This compound has inner chain 2 carbon atom, including the cyanide carbon. So this is an ethane nitrile. In this ethane nitrile, we have a hydroxyl group. So the name is going to be hydroxyethane nitrile. Next, we go to another aldehyde. The aldehyde having 2 carbon atoms, it is ethanol. You can see a CH3 group attached to the carbonyl functional group. If this compound reacts with HCN, you get another compound, and it is called hydroxypropane nitrile. Let us see the structure of this hydroxypropane nitrile. You can see in this compound, including the carbon in the cyanide group, there are 3 carbon atoms attached one after another. Carbon 1, carbon 2, carbon 3. And in this carbon chain, on the second position, we have an OH group. I have written the name hydroxypropane nitrile. Actually, this should be 2-hydroxypropane nitrile. 2-hydroxy, because hydroxyl group is attached to the second carbon. So remember, when you write the name of this, it should be 2-hydroxypropane nitrile. Now let's move on to the reactions of ketones with aqueous HCN at the presence of cyanide catalyst in alkaline medium. I'll take propanone for the reaction. Propanone is the simplest or smallest ketone. It has 3 CH3 groups attached to carbonyl functional group. If this particular compound reacts with HCN, what will happen? Another hydroxynitride will be formed. The structure is this. If you figure out the name for this, we have cyanide, carbon, CH3. The molecule has 3 carbon atoms in a row, so it is a propane nitride. In this propane nitride, there are 2 substitute groups, OH and CH3. Both are present in the same carbon, carbon number 2. So the name of this is going to be 2-hydroxy, 2-methyl propane nitride. The name has to continue here. There's no gap. Afterwards, we go to another reaction. What is this ketone? This ketone has 1, 2, 3, 4. It is butanol. If butanol is reacted with HCN, you can just figure out what is going to happen. 1 hydrogen comes to this oxygen, which is in the double bond, and this carbon in the functional group is going to get attached to cyanide functional group that we use here over here. In the earlier slide, I told you that the speciality about these reactions is that the carbon number of the product is going to be 1 more than the carbon number of the reactant. You can see this here. See, methanol has 1 carbon atom, but its product hydroxyethane nitrile has how many carbon? 2 carbon atoms. Similarly, ethanol has 2 carbon atoms, but hydroxypropane nitrile has 3 carbon atoms. See, it's very, very clear. 1 carbon always gets added. And then propanone has 3 carbon atoms. Prop means 3 carbon, but it is going to a compound having 4 carbon atoms. And butanone has 4 carbon atoms, and its product, when it reacts with HCN, is going to have 5 carbon atoms. So this is a very, very important point you must remember. This is a very, very good reaction to increase the carbon number of a molecule just by one atom. So these are one type of reaction shown by both aldehydes and ketones. This is pretty simple. And afterwards, we go to another reaction type shown by both aldehydes and ketones. And this is the reduction of aldehydes and ketones using reducing agents. We have 2 commonly used reducing agents to react with aldehydes and ketones. First one is lithium aluminium hydride in dry ether. This lithium aluminium hydride is a highly unstable substance. You can't add lithium aluminium hydride into an aqueous medium because it reacts with water. So we have to use it in dry ether. Dry ether. Ether is a solvent. We don't discuss this ether in our syllabus, but then ether is a kind of an organic solvent, colorless solvent. We use it to mix or dissolve other reagents for chemical reactions. Second one is NaBH4. NaBH4 can be given in ethanol medium. This is called sodium borohydride in ethanol or lithium aluminium hydride. Even though you don't remember, it's easy to remember, but then, yeah, try to remember this lithium aluminium hydride and NaBH4. There's something very, very important. What is this important? Okay, when an aldehyde undergoes reduction with lithium aluminium hydride or sodium borohydride, aldehyde, they make primary alcohols. If you don't remember what primary alcohols are, I have given a structure of primary alcohol on the right-hand side. OH group is attached to this carbon. This carbon is an alpha carbon. Alpha carbon is attached to only one alkyl group in primary alcohols. Similarly, if you go to reaction with ketones, reduction of ketones, ketones can be reduced to secondary alcohols. Don't forget, aldehydes produce primary alcohols, ketones produce secondary alcohols. I have given the structure of secondary alcohol, where you can see OH is attached to a carbon, and this carbon is attached to two R groups, two alkyl groups. So first one is a primary alcohol produced by aldehyde. Second one is a secondary alcohol produced by ketones. Remember, we can't make tertiary alcohols by this reaction. Aldehydes and ketones always give primary alcohols and secondary alcohols. That's it. Similar to the earlier case, we'll try to find out how aldehydes can be reduced with lithium aluminium hydride in dry ether or sodium borohydride in methanol. I'm taking again methanol, one carbon containing aldehyde, of course, the simplest aldehyde. If you react this methanol with lithium aluminium hydride or sodium borohydride, aldehydes go to methanol. Remember, because it's an aldehyde, this methanol is going to be primary alcohol. See, how is it happening? Oxygen in the carbon double bond part, the functional group, oxygen gets a hydrogen atom, and this carbon is getting a hydrogen atom. Two hydrogen have come into this. It's a reduction reaction. And let's take another example. As usual, we take ethanol, two carbon containing aldehyde. What will happen? This oxygen will get one hydrogen. Carbon also will get one hydrogen, making a compound called ethanol. Ethanol is also a primary alcohol because its alpha carbon has only one alkyl group. This is how aldehydes react with lithium aluminium hydride or sodium borohydride. Remember these two compounds. Now let's move on to the reduction of ketones with lithium aluminium hydride or sodium borohydride in methanol. For the discussion, I'm taking propanol. Propanol is a ketone with 3 carbon atoms. The structure is given here. What will happen when you react with the reducing agents given? It is going to be propan-2-ol. Propan-2-ol has 2 alkyl groups attached to the alpha carbon, so it is a secondary alcohol. So we call it propan-2-ol. It's a secondary alcohol. And let us talk about another compound. We talk about the reactions of butanol. Butanol reaction with this lithium aluminium hydride or sodium borohydride is going to produce another secondary alcohol. What's the name of it? Butan-2-ol. 1, 2, 3, 4. 4 carbon atoms are there. On the second carbon, we have OH group, so it is butan-2-ol. Here I have given the hydrogen atom white, in all the others it's red. There's no special reason. This also should be actually red, but you understand the concept. See, aldehydes always produce Y reduction primary alcohols. Similarly, ketones always produce secondary alcohols by reduction. It's very easy to understand. You don't have to think about it too much. It's a very, very simple thing. Okay, this is also a reaction shown by both aldehydes and ketones. We completed 2 reactions, and we are coming to the last reaction. And in the last reaction, we talk about a reaction of aldehydes and ketones with something called Brady's reagent. But commonly we know it as 2,4-DNPH. You have to know how to draw the 2,4-DNPH structure. It's a bit of a complicated thing if you don't know how to construct it. So I thought of giving you a step-by-step approach to construct the structure of 2,4-DNPH. First, I start the work by drawing hydrazine structure because this name is 2,4-dinitrophenyl hydrazine. Hydrazine is a compound which is undergoing some changes in it to make this 2,4-dinitrophenyl hydrazine. What is the structure for hydrazine? It is this. We can call it NH2, NH2. The 2 nitrogen atoms in the middle are bonded together through a single bond, and each nitrogen is bonded to 2 hydrogen in turn, hydrazine. Now, I can modify this hydrazine a little bit to make phenyl hydrazine. What is the meaning of phenyl hydrazine? Phenyl hydrazine means to this hydrazine part, we can remove 1 hydrogen and attach a group like this. This is actually, we call it aryl ring. It is actually a benzene ring. We can attach a benzene ring. We don't want to talk about this structure very much now because in A2 chemistry, we talk about the benzene structure. Actually, here we have 6 carbon atoms. 1, 2, 3, 4, 5, 6. There are 6 atoms. You can see a hexagon over here because it's a 6 carbon, actually a ring. When this 6 carbon ring gets attached to hydrazine, this group is called phenyl group. So phenyl group containing hydrazine is called phenyl hydrazine. But still we have not come to 2,4-DNPH yet. I go one step ahead now. Now I'm going to construct 2-nitrophenyl hydrazine. First I take hydrazine. And as earlier, I will attach phenyl group into this. They are the phenyl group. And in this phenyl group, I said there are 6 carbon atoms. We can start counting the carbon number, labeling the carbon atom to which the hydrazine part attached as number 1. Here we have number 1. So number 2 comes over here. See, number 2. When I say 2-nitro, it means to this second position, carbon number 2, a nitro group is getting attached. Nitro group means an NO2 group. This bond actually, I have considered NO2 as a single group, but actually this bond has to come to nitrogen, remember. Bond has to come to nitrogen if we draw it very, very accurately. So this is 2-nitrophenyl hydrazine, but what do we have to draw? We have to draw 2,4-DNPH. So what's the meaning of it? Dinitro. Dinitro means there are 2 nitro groups. Oh, what are those 2 nitro groups? Again, when it comes to 2,4-dinitrophenyl hydrazine, I construct the hydrazine structure, but 1 hydrogen is missing because to that hydrogen I had to enter a phenyl group. Now in this phenyl group, we have carbon number 2. To this carbon number 2, we have to attach 1 NO2. Again, this bond has to come to nitrogen. If the number 2 carbon is over here, the name says 2,4-dinitro. It means on the second carbon, which I have shown here, there's 1 nitro group. Dinitro means there's another nitro group on the 4th carbon. Where's the 4th carbon? 4th carbon is over here. To the 4th carbon, 1 NO2 comes. Now, this is a structure we identify as 2,4-DNPH. please know how to draw the structure. In order to help you how to draw this 2,4-DNPH structure, I constructed the structure starting with the hydrazine, the simplest basic molecule. Actually, this 2,4-dinitrophenyl hydrazine is kind of a yellowish orange solution. We use it as an identification in identification test. It can help us to identify aldehydes and ketones from other organic compounds. Aldehydes and ketones can react with 2,4-DNPH solution. What's the color of 2,4-DNPH solution? Yellowish orange. Aldehydes and ketones can react with 2,4-DNPH solution to form an orange precipitate. This is a very, very unique observation. If you add an aldehyde or a ketone to 2,4-DNPH, definitely a yellow or orange precipitate is formed. And how is this reaction happening? I can explain this in this manner. Now, this is a ketone or aldehyde. This is a ketone because there are no hydrogen attached to carbonyl functional group. And because this has 3 carbon atoms, it is propanone. If I bring this propanone molecule nearer to this 2,4-DNPH, see what happens. The oxygen atom in the carbonyl functional group and the 2 hydrogen atoms attached this nitrogen N, they join together. If they join together, 2 hydrogen and 1 oxygen, water molecule will be produced. When the water molecule goes out, the remaining parts of the ketone two parts are going to join together, making this special compound. See, when this carbon atom over here in the ketone join with the nitrogen in the 2,4-DNPH, a double bond is created between them. And this has a very nice color, a precipitate. See, this is the color of the precipitate form. So when you add, actually this is a propanone. When you add propanone into 2,4-DNPH, you get this colored precipitate. So this is very, very an impressive thing in a laboratory, one of the most beautiful things you can see in a laboratory. So we are in the reaction shown by both aldehydes and ketones. Let us see a simple question. Try to sketch the product obtained when butanone is reacted with 2,4-DNPH. Butanone is a ketone having 4 carbon atoms. And if you go with 2,4-DNPH, what will be the product? Take a piece of paper and sketch the structure of the product. Probably I can give 20-30 seconds. See how efficient you are. Okay, I think you were able to figure out the product structure. See whether you were able to figure out this. Yeah. Okay, children, in this video, the main focus is on the reaction shown by both aldehydes and ketones. This is kind of a colorful lesson, and it is also important for your AS exam and A2 exam. Probably in the next video, I will talk about some more reactions of aldehydes and ketones. What I'm trying to say is that's all for us in today's session. Yeah, before I finish, you can remember this also. 2,4-DNPH is used to distinguish aldehydes and ketones from other organic compounds. If somebody asks, how is it going to be? I can go back a little bit and show you. See, when you add an aldehyde or a ketone to 2,4-DNPH, you get a red-orange precipitate. That's how we identify an aldehyde or ketone by using 2,4-DNPH. I think that's it for today's session. I should thank you for learning with EasyChem. Have a good day.